In this video, we're going to talk about greedy algorithms in the context of a problem called activity selection. Suppose that we have a lecture hall and we have multiple classes that need to meet in that lecture hall, and the class times possibly overlap. So, for example, let's consider the following courses. So we have course 1, 2, 3, 4, 5, and 6. And each course has a start time and a finish time. So the start time for course 1 is 0. The finish time is 2. And we fill it out the rest of the way here. 2, 5, 3, 5, 3, 5, and 5, 6. Actually, let's make this 2, 5. Okay, so what we have is we can make a timeline here. Times 0, 1, 2, 3, 4, 5, and 6. And if we plot these courses, it looks something like this. That's course 1. Course 2 goes from 1 to 3. Course 3 is from 2 to 5. Course 4 is from 3 to 5. Course 5 is from 2 to 5. And course 6 is from 5 to 6. Now, our goal, our task, is to find the maximum number of courses that we can schedule into this lecture hall. And looking at it, we think, okay, well, probably course 1, 4, and 6, and we won't have any overlap. But we need an algorithm to be able to do that. So our goal in activity selection is to find the maximum set of mutually compatible activities. So, for example, activities 2 and 3 are not mutually compatible. They overlap, so they can't both use the lecture hall. So we want to find the maximum number of courses that can use the lecture hall, the maximum set of mutually compatible activities. We are going to call AI course I, or activity I. So AI is the ith activity. Now, could this be solved with dynamic programming? Well, one thing we need to show with dynamic programming is if it has optimal substructure. And a reminder about what optimal substructure is: the solution to a given subproblem, the optimal solution to a given subproblem is always the same. Now, we want to find out if activity selection has optimal substructure. Let's define S sub ij as the set of activities that start after AI finishes and that finish before AJ starts. Okay, what does that mean? Let's draw a picture. So here we're going to have activity AI. Over here we'll have AJ on the timeline. Then we're going to have some activities in here. Okay, so what is the set SJ? Let's do one more here. No, let's not. Okay, what is the set SJ? Well, it's all activities that start after this point and end before this point. So the last activity there overlaps AJ, so it's not in SJ. So this is Sij. Okay, now we want to define Aij to be the maximum set. From all Sij. So what would be the maximum set here? Well, there are actually a couple of choices. Change colors. But let's say this is a maximum set right there. We can't have all three because they're not mutually exclusive. Okay, now let A sub k be in the maximum set. So maybe we're going to let A sub k be, I don't know, that one right there. Now we can split it into subproblems. If we know A sub k, which is some activity in the maximum set from Sij, then we have two subproblems. We have S from I to K and S from K to J. Then, so all of these activities are before, so all of these activities are before A sub k. So here's A sub k. So we're going to look at all of those before, and then we're going to look at all of those after A sub k. So this is subproblem number 1, subproblem number 2. Therefore, the final answer, the optimal set, so A from 0 to n, is going to be Aik, which is the answer to that subproblem, unioned with the kth activity, right there, unioned with the optimal solution to Akj, right there, which is all of these. So how would that look in dynamic programming? It might look something like this. Here, let's just do pseudocode activity. We're going to have an array of activities. We're going to have I, J, and some optimal solution. So let's set some max m value to 0. Then we'll look at every k and we'll say n equals the activity. So now we're doing the subproblems, passing the array. We'll go from I to k minus 1, and we'll put that solution in solution A, plus call activity for the other subproblem, A. Now we go from k plus 1 to j, so on the right-hand side, and we'll put that into solution B. Plus 1 for A sub k. Now, if n is greater than max n, actually we wanted to do max n here, not max m, then we'll set the new best solution to n, and the solution is going to be the solution of the left subproblem plus the activity we found plus the solution to the right subproblem. And then we would return the size, the number of activities. So this is a dynamic programming solution. And it works, right? We've got our two subproblems, but it turns out that there's a better way, and that is the greedy approach. What we're going to do is first, we're going to sort activities by finish time. Then we're going to choose the next available activity. What do I mean by next available? I mean the next activity in the list that is mutually exclusive with all existing activities. So here's an example. So here we have an activity, we have another activity, and another activity. Okay, now you can see these activities are sorted by finish time. As we go down through the activities, all the finish times are monotonically increasing. Okay, so the greedy algorithm says choose the first activity. Then choose the next available activity. Is the next activity available? No, because it overlaps with the first activity. Here's the next available activity. Then, is the next activity available? No, it overlaps with that activity. But this one's the next available, and then we can't use that. And it turns out that this is an optimal solution. These three activities here. That's the greedy approach. Super simple, and amazingly, it finds the optimal solution. So, I say that it finds the optimal solution. We need to prove it. So, does it work? Here's a theorem. Let S sub k be a set of activities. And let some activity A sub m be in S sub k, and let it have the earliest finish time. Then A sub m is in a max subset of A sub k. So A sub k is the optimal solution, maximum number. And there could be more than one, right? You might have 3 different activities that would, or you might have one solution that has 3 activities and another solution has 3 different activities. That's totally possible. Well, all we want to show is that if A sub m has the earliest finish time in the set of activities, in the ordered set of activities, then A sub m is in a max subset of AK. And if that's true, then the greedy algorithm works. Here's the proof. So we are going to let A sub j be in the optimal solution. And it's going to have the earliest finish time. We want to show that we can replace A sub j with A sub m. Which means if we can replace A sub j with the one with the earliest finish time in the entire set of activities without messing anything up, then we can show that A sub m is in the optimal solution. So, suppose they're not equal. If they are equal, then we're done. So it's not interesting. So let A prime sub k be A sub k with A sub j replaced by A sub m. Okay, what does this look like? Let's consider A sub k. So we have some A sub j there, and then we have a few other activities going on. They don't overlap, and we're given that A sub k is the optimal solution. And this is disjoint by definition. All right. Now let's replace A sub j with A sub m. Now, before we do that, let's draw all the other ones. And let's think about this. A sub m is an activity that's in the set of all activities. And we know that A sub m, let's see here. Here we are. A sub m has the globally earliest finish time. So its finish time is either equal to or earlier than A sub j. So A sub m is going to look something like this. And here is A prime of k. So, what have we done? Well, first of all, we know that A sub k is disjoint because the finish time of m is less than or equal to the finish time of j, right? This finish time is before or equal to that finish time. And we also know something important, that the number of activities in A sub k in that optimal solution is exactly equal to the number of activities in A prime. So, A prime sub k is a maximum, and it has A sub m. And we've proven the greedy approach. That we can take any optimal solution, we can put the first activity with the activity with the smallest start time in, and the solution is still going to be optimal. Now, let's look at, very briefly, the two solutions that the book gives. The first is a recursive solution, and so here we have the start times, we have the finish times, we have k, which is the where we're at in the array. So we're going to step through the array, and then we have the total number of elements in the array. We look at we're going to find the first activity in SK to finish. So here we have M. We're going to start M after K. So here's our array, and here's K, which is where we're going to start. And we're going to step along here in the array until we find an activity that starts after the kth activity finishes. So while our start time is less than the finish time of k, we're going to loop. So after we've ended the loop, either we're at the end of the array, in which case m would be equal to n, or s sub m, the start time of m, is greater than or equal to the finish time of k. And so we found the next available activity. After we've done that, we simply make a recursive call. So that's the recursive formulation. But the nice thing about greedy algorithms is we can have iterative formulations. And here's the iterative version. We start with k equals 1. We're going to iterate to the end of the array. If we find one that is greater than the current activity that starts after the current activity finishes, then we go ahead and add that one, update our current activity, and we're done.